Hello, welcome to my talk about are you using in Samba and the status update of it. My name is Stefan Metzmacher. I'm working for SerNet and I'm a member of the Samba-Team. So the topics for today are basically a little overview of what are you using is, how we use it in Samba, some performance research and prototyping, the road to get things upstream and what we need to do in future. And at the end or during the talk you can ask questions if you want. So I gave a similar update in 2002, 2020, 2021 and earlier this year also at Samba XP. So just going to the milestones for 13, for 15 and for 19, which is the current version. And now I have a little update on what we've done compared to the Samba XP talk. So what is are you using? It's a new scalable async I/O infrastructure for the Linux kernel. It's based on submission queues and completion queues. And these queues are memory mapped between kernel and user space. That means we don't have to copy things around for the syscalls, and you can do batching and avoid syscalls in a few cases. So if you're more interested in the details, there's a great LWN article on that. And the good thing is that it integrates nicely with our async t-event model we use in Samba. So it may delegate work to some kernel threads, but for most things it tries to do in-kernel async stuff with completions in the main thread. So the things we could use between user space and file system, which are available from the start in Linux 5.1, are basic things like readv, writev, fsync, and from newer kernels, it's setxutter, getxutter. Under discussions is a get dends, but that's not upstreamed yet. And also from a 5.6 kernel, effort-wise. Some path-based operations which we could use in Samba is openadd2, statex, some personality registration. That means we could impersonate different users without using setGUID and something like that. Then there is unlink add, rename add, and so on. Basically, most of the syscalls you would normally expect from a file system. So, between user space and the socket, we have send message, receive message, which improved over the time in the kernel, also allowing wait all support. That means if not all data is there you wish for, we will wait in the kernel until it's there. And also if that's not possible, you will break possible batching. So you can link requests together in order to run them in a specific fixed order. And if the first one fails with that, then it will not continue. That makes it easier for user space to deal with. Then we have splice and T there, which is basically the same as the syscalls. And relatively new in the 6.1 kernel, we have send message with zero copy. That's basically similar to the send message syscall, that uses a special flag message 0 copy. But the good thing is that the notification of completion is much easier with IOUring, because we will just get a second completion event in the completion queue, and that makes it much easier to deal with. There are some discussions about a get buff operation which could replace splice, but I don't think that gets anywhere currently. So the history with IOUring in Samba started with the 4.12 release, where I added IOUring VFS module to Samba, which uses the pread, prewrite, and fsync calls, and that is basically there in order to replace the thread pool we are currently using in the default backend. And that showed minor improvements, changing speed from 2.2 gigabytes to 2.7 gigabytes per second for the test I did at the time. So it improves a bit, but it's not much. Basically just avoiding thread overhead in the user space. Yeah, and it avoids the context switches there. But the data copy still happens, and the CPU is busy doing mem copy things. Yeah, in October 2020, I was able to do some experiments with a powerful server that had 100 gigabit interfaces and numerous nodes per server. And with that, I was able to explore how we could more or less accelerate the network link. At the time, I just focused on the read performance, because that's what typically more important and is used more often and what easier to implement. And we basically tested with a Windows client. Further details can be found on that link if you are interested. So the basics of it is I analyzed the performance just using the current Samba code, which uses send message to push data back to the client. And with that, and our thread pool in Samba doing the I/O, we had 4 connections using multi-channel from the client, but it was only possible to get 3.5 gigabytes per second out of it, 3.8, and basically 5 CPUs were completely busy with it. And a large problem was that the send message call itself took half a millisecond to complete, and that added latency and so on. And the first thing I tried was to use the IOUring send message call in order to defer the mem copy on the server to a different thread in order to get some more bandwidth and latency reduction in the main thread. And with that we get up to 6.8 gigabytes. And the main SMBD just used 11% of one CPU, but the worker threads in the kernel, they use still the mem copy, but the overall reduction was that only 3 CPUs were basically busy. Yeah, that's basically the same. And here with perf-top we see that the copy user enhanced fast string takes most of the time, and that's basically mem copy. So then I tried send message for just the header and splice for the file data, and that reduced the overhead drastically because we no longer need to copy things around. And for that, basically the limiting factor was the Windows client, so I changed that to use 16 connections in parallel, but still it was just able to get 8.9 gigabytes per second, and the main SMBD was down to 5% of one CPU, and with all the helper threads we were basically utilizing one CPU. And in order to overcome the problem with the Windows client, I used test with SMB client, and there I started 4 SMB client binaries using multi-channel for the same connection, so they ended up in the same SMBD process, and with that I was able to get more or less network bandwidth. So 11 gigabytes per second is what we got, where SMBD was just 8.6% of one CPU, and the rest was basically 20% per CPU for 4 threads there. So that was a huge improvement, but the problem is that we can't use splice, and I will go to that later. So if we look at the output of the perf top and so on, we see that we still use a little bit of copying, but not that much. Basically, that copying is on the client side because we tested with loopback and 8 connections there, and we were able to even get 22 gigabytes per second just doing loopback. So a while later I did the same experiments with a more powerful server and get even better numbers, and I implemented a prototype with the SMB write side, where we use receive message and splice in order to get data from the network, and then use splice to put it into the file system. That also got very good numbers. And yeah, basically the bottleneck was always on the client side, where we didn't use any optimization. So there we still use the mem copy and so on. And in future we may change that to also use things like splice and so on, so that we can max out more on the client side. So in order to get things upstream, we need an addition to our T-event library, where we need a way to just react on errors on a socket and not get notified when there's incoming data, but only when there's an error, so that we can close the connection, and all read and write will be handled with IO during send and receive message. So there are 2 merge requests up there, which are hopefully merged soon. So the abstraction we will have in Samba is that we can we have a Samba IO ring subsystem, and basically we will attach that to a T-event context. So in our stack we typically pass down the T-event context to all layers, and with that we would be able to get the IO ring context from everywhere in the stack in order to use it. Then we have a function to get features, and so that we can at runtime detect what we can use and what we can't use based on what we find in the kernel. And that makes it much easier to code and avoid if-defs in the code. And for now we will use, I call it hybrid t-event backend. It's basically still using equal-weight as blocking call, but on top of that we will be able to use any IO-ring stuff. But that makes it easier because the poll implementation in IO-ring doesn't fit to what we need. So in order to create a request, we have two structures, a completion and a submission, and prepare functions for that. And then we can just queue them together and call submission SQE to get the SQE structure, the native one, and fill that. And then we queue the submission to the context, and then it will be processed by t-event internals and get the completion called eventually. So the tasks are to convert the existing VFS IO ring to it. That's more or less done, but it turned out that there were some performance regressions, and I need to optimize some things in the new code in order to have the same performance characteristics. But I hope that will be done soon. And then we have the code in the main SMB2 server to do the socket-based stuff with IO-ring. I have the prototype for that, but that needs further cleanup, and also we need to check that we don't regress performance for other workloads which are not I/O intensive. Yeah, basically refactoring to use send and receive message. And the sad thing is that what I used in the prototype was send message and splice can't be used because I found out that when you splice from the file system into a buffer and then to the socket, during the socket operation the page cache may change unexpectedly behind us, and that would mean that more or less SMB signatures or something like that will be invalid, and we return unexpected data. So we may add that with a special option. So it's basically the same problem with our send file implementation, which we could activate if administrators want to, or maybe we will just use it on read-only files or so. But the good news is that we have now the send message with zero copy command in IO-ring, and that means instead of using two copies, one from file system to the buffer and then from the buffer to the socket, can be reduced to just one copy, and that helps a lot. It's not as perfect as with splice, where we have no copy at all, but at least it reduces CPU load drastically. So I was just testing it yesterday using a custom kernel, because by default if you go loopback or between some containers on the same host, you're not able to use it. It will always copy data, because otherwise the same pages would be available in two containers or in two processes, and that's a security problem. So, but in order to test it, I changed the kernel to remove that restriction and with a file system behind it, I was able to increase the throughput on read from 3.5 gigabytes to 7.5 gigabytes per second. And then I thought it would be good to see the difference just without a file system behind. So I just changed the VFS module to don't touch the buffer at all and just return success. And with that, so the boundary between the buffer and the socket is changed from 6 gigabytes per second to 18 gigabytes per second. So the bottleneck is really the file system and the infrastructure with the send message zero copy is very good to use. So in order to get things upstream, I already added some of it to upstream, preparation patches, restructuring the code in the main SMB2 server. I even have automated testing now in place for the VFS module, but the rest of the changes needs a bit more work in order to avoid these performance regressions. And in far future, what we could also do is in SMB client code, because we pass down the T-event context everywhere, we would be able to use this IOU ring event context scattering in order to make use of it down the stack there. Okay, so that's all for today. I'm a bit surprised that it was so fast, because last time I did more or less the same presentation. It's taking much longer. Yeah, in the back.
So two questions. So one is with the socket bound you are now doing truly zero copy.
Yeah.
The performance data you showed it's throughput bound, right? So
yeah.
You mentioned the increased throughput is mostly because of reduction in CPUs and not exercises and all that.
Yeah.
Now, if you give enough CPU to Samba, can you still achieve same throughput with everything else remaining same? In number of multi-client, multi-channel connections, all that, right? Can you still achieve the same throughput with P-read and P-write instead of IOU?
So the question, if it would be possible to use to achieve the same performance with just P-write and P-read and so on, maybe if we would put them also the send message code into thread pool or something like that, but still the CPU usage would be very, very high, and it's likely that we still bound for the CPU.
But it's worth trying out, giving it. I mean, let's say we don't have the implementation ourselves,
yeah.
And we want to give it, and it's Samba equivalent, right? In terms of how our stack is looks like, right? And we give it enough CPU, and also make sure rest of the system scale with respect to number of connections, all that, right? Ideally, I should be able to get the same.
Maybe not the same, but at least much higher than it's currently.
Okay. One more question. So, we done any latency sensitive test, because that's where you see the real use of IOU, because you're avoiding a lot of these. The latency part goes down, right? With the lack of context is down, right?
Yeah.
Anything with random reads and smaller IOs that you've seen with IOU?
I don't think, so the question is if there are improvements even for small IOs with IOU ring. And I'm not really sure there is, because maybe if you have a larger queue depth in your IO, that may be able to make more use of it, but basically if you use IOU ring for very short IOs, it may just add latency, but I recently added some improvement to avoid that, so that we're at least as fast as a pure pre-write and pre-read, which are in the main process, not in the thread pool.
That's one more question. So, in your token side, have you tried RDMA or Samba today doesn't support RDMA?
I have a prototype of an RDMA module for the kernel in order to use that, but that's far away from getting finished. So I concentrate first on these things, and maybe after I have everything upstream, I could work on that again in order to...
I want to ask why you think the Samba client doesn't support RDMA. It does.
I was talking about the server side.
Server side, okay.
Yeah, I mean, strictly the Samba client doesn't use RDMA. It's a kernel client.
Linux kernel client does support
Yeah,
RDMA.
yeah.
Yeah, we definitely have that.
Oh, okay.
Yeah.
I was talking about Samba.
It doesn't need IOU ring because it uses the native RDMA API, which is basically very similar.
And anybody who's got extra cycles and can help, what I would love is if we took the RDMA code out of the kernel sys code and the kernel ASMD code and made it available for Samba and made it easier for guys like you to look at.
So Steve, that's his project is.
Exactly,
Yeah.
exactly. And I think that that's unbelievably helpful, and anybody that's willing to help them, this is a grand slam home run, because if Samba can use that and the client can use that, bugs go down, and it helps our performance a lot.
So, just to repeat what was just discussed, there was a discussion on using RDMA for Samba, and Steve and Tom discussed that. It would be good to share the implementations between the sys server KSMBD and the client side, and also with user space, and that would be the way forward. Jeremy?
How does the impersonation on IOU ring work for the path-based calls? Because that's the key to getting great performance for create and bundling, which right now we make.
Yeah, so the question is how the impersonation works for things like OpenAD2 or so. And the thing is that you would do set GUID, set UID calls and so on, and then call the IU ring register personality call, and that gives you an integer number, and then you can in each individual, so internally in the kernel, that captures the current credentials, reference it in a table with the index, and then you can use that number on each individual request, and then in the kernel it will just impersonate before the call and back. Yes?
So recently, June, Google said they disabled IOU ring on their production service and a bunch of other things due to security vulnerabilities. Does it affect your work? What do you think about the adoption of IOU ring?
I mean, if they think that's a security problem, that's, I don't know. So with the in the 5.12 kernel, the model was drastically changed. So before, there were a number of helper threads in the kernel which were not attached to the process and shared between processes. But the model was changed due to security problems, and now the helper threads in the kernel are basically the same as using a clone syscall to clone the application, but they just never return back to user space. But otherwise, accounting-wise, security-wise, they are just threads of the main process. So, and I don't see any security problem with that. So, yeah. Any further questions? Okay, thank you for your attention.